Thank you for being here. So I'm going to be talking today about neuroevolution and specifically evolving neural topologies. So artificial intelligences are a growing part of our life. We use them every day, really. So what this talk is going to cover is what are artificial intelligence, what are neural networks, and how can we kind of evolve these neural networks to do whatever task we want. So first, a little bit about me. This is me, and that's my wife. I help people who are frustrated with complex problems, specializing in software. I have two different resources, my website as well as my GitHub. And we went over this, but we're going to go over what is a neuron, what is a sensor, what is an actuator, what is a neural network, and what is evolution. Finally, what is neuroevolution. Where to start? OK, so originally where I learned about this was through this book by Gene Scher. In 2010, he created the DXNN system in Erlang. And this book explains that. I then created a prototype in F#. It's called Neurofish. It's all open source, as well as Elixir, Evolixir, which is built-in Elixir. And for those who don't know, Elixir compiles down to Erlang bytecode. The brain. So what is the brain? It's a very exciting thing. It powers our everyday movements, our everyday actions, our everyday judgments. And it's really just made up of a bunch of neurons. And a neuron consists of a cell body with dendrites going into that cell body. These dendrites connect to different neurons, and they receive electrical synapses, as well as chemical ones, into the cell body, which all gathers at the axon hillock. The axon hillock is like it's a disk, and the reason for this is that the neuron is an excitable cell. That means that if it hits a certain point, it's going to become excited. It's going to express its excitement to the other neurons that it's connected to. In order to accommodate for the latency that we experience with reality, in all these different dendrites, we need to gather this electrical synapses at this axon hillock, which is simply a disk. And imagine these electrical impulses coming down into this disk, and it's spreading out across the surface area, the electrical values, I would say, in which after it reaches a certain point and becomes excited, it's going to send an electrical synapse along its axon to its axon terminal, which connects to other dendrites on other neurons. We can express this in our architecture like this. We have inbound connections, being if we express a neuron as maybe a process, agent, or a mailbox processor, then we can receive messages, and we're going to expect those messages from whatever we define our inbound connections. We collect those synapses in the barrier to accommodate things not happening exactly at the same time. When this barrier is full, we then calculate the output synapse, and we send it to all the outbound connections. There's a little bit more to this. So when we receive a synapse, it's a raw synapse value. However, in the biological neuron, a dendrite can go either pretty far into the cell body or not so much. And we need to express this kind of, this fluctuation of electrical energy as a weight. And so we express this as a neural connection weight. And simply put, the weighted synapse is equal to the raw synapse value multiplied by the neural connection weight. This allows us to learn. So for example, let's say you're learning how to how to use a wrench or maybe play the guitar. Over time, your movements, your thinking, your visual perception, your hearing perception, that all becomes very fine-tuned. You could think of this as your neural connections becoming very precise to whatever value you need to actually be able to do that correctly. This is just more of a demonstration of the synapse coming in, and then it's multiplied by the weight. So besides that, there are a whole bunch of neurons, but how do these neurons actually get values? It gets values from sensors, things like eyeballs, stuff like that. And a sensor has one job, to synchronize. Whenever we synchronize all of our sensors, it pulls in sensory data and it pushes it across the neural network. And this looks like this, where we have a vector of data, and we take the first piece of data from that vector, and we send it to the first neuron. Take a second piece, second neuron, and third piece to the third neuron. This is an important thing to keep that order, because as we're evolving the neural networks, we need to have some type of consistency of how does the neural network understand what this data is going to do to which neuron. So a neuron has a function flow. And it's simply put, there's a barrier that receives a whole bunch of inputs and then takes all of those inputs once it has its full, and it sums them. After it sums them, we pass it to an activation function, which is completely configurable by the researcher or the programmer, whoever is running the simulations. After that, we output that sum, that modified sum value, to all of the outbound connections. Another example of the activation function is that we could take a large number and bound it between 0 and 1. It's really whatever you want to do to understand kind of the optimization and the functionality of your brain or your neural network. So the actuator is like an arm. It's something you act upon. And the actuator is very similar to a neuron. It has a barrier, and it receives a whole bunch of messages, or it receives a whole bunch of synapses from the neurons, and then it sums them. However, it doesn't run it through an activation function. Instead, it passes it to a high-order function that we have defined called an action function. And the action function is, it pretty much says, OK, you're an arm. This is how you're going to function. You're receiving this float value, and you're going to act upon it. So this is a basic neural network setup. We have a sensor which synchronizes, and then sends it along to the first neuron layer. It goes to the next one, goes to the actuator. It's a very basic one. It's called the feed-forward neural network. But that's not really how our complexity works. We actually have a lot of recursive connections. And recursive connections are simply put, our sensor synchronizes, it goes to the first neuron, and that goes over here to the second neuron. However, the second neuron has a connection to the first neuron. And so that synapse value, or the outbound value of that second neuron, is going to be stored for the next cycle of the neural network. This is effectively a memory circuit. Evolution. This is very exciting for me. So evolution, we've evolved over millions of years to where we are now to be able to think and to do the things we can. And how does it work? And more importantly, how can we use this concept to get to a solution, a neural network that is intelligent enough to operate in the environment we set for? A really great example of this is dodo birds. So we have a dodo bird, and it has a couple of offspring. And these offspring are all mutated. We've got an offspring with a different color, offspring with a hat, and an offspring that yells at us. So essentially, we pass these offsprings into a simulation. And after they're done in that simulation, we pass them into a fitness function. A fitness function essentially says, this offspring scored this amount. So that way we can compare how well did this dodo bird with the hat do versus this dodo bird who is able to talk. And the big thing about this is, in real life, is that evolution, or a fitness function for reality, is how many offspring did you have, how successful were those offspring in passing on their genes as well. And so we're able to score these different dodo birds, these offsprings, with our fitness function. This bird that was able to talk ended up scoring very high. And the bird that was a different color also scored pretty high. So if we were going to say we want 2/3 of our offsprings, our solutions, to continue on and pass their genes or their makeup, essentially the colored one and the one that speaks are going to win. Poor dodo bird with a hat. So we have topology mutations. This is how evolution the concepts of that, of mutations, kind of go into neural networks. I showed you before a basic neural network connection. We can apply these mutations to that neural network after it has run to find offspring that could potentially perform better than its predecessors. A good example of this is the add neuron mutation. So the add neuron mutation is very simple. It randomly selects inside of the neural network a neural layer to add a neuron to, and then it randomly connects that neuron to any other node inside of the neural network, and then it connects it to an output node. We can do all sorts of things with this. For example, add sensors. So let's say that we have a robot that's able to just roll forward. That means it's got an actuator, it's got wheels, and we want to get it to learn how to use its eye. So essentially, we could give it a color sensor, and we could get an infrared sensor, and instead of defining how exactly this neural network is going to work, how exactly these sensors are going to be connected into the neural network, we simply introduce it into a long generative simulation in which we're expecting at some point that the solution is going to learn how to use its sensors to be able to operate. It might not, though. That's the big thing. Life simulation. All right, so a basic very concept of life is eating. It's energy. We need it to act, we need it to grow, we need to consume things to be able to gather energy forth. And so there are some rules to this simulations. For example, entities must have a finite lifespan. That means they need to die after a certain amount of time, and this is essential to stop them from keeping further solutions from evolving. And the second thing is that entities must have an energy cost when they act, and it needs to also have an energy cost as time progresses. Also, food must be available, the right amount of food. If there's too much food available, then that means the solutions won't need to work as hard to get that food. If there's not enough food available and there's a lot of entities, that means the entities need to compete against each other over the food. So Gene Scher created this simulation in DXNN. It's pretty cool. It's just simple food gathering techniques. Let's see, I'm going to need to exit out of the slideshow. Give me 1 second. All right. So this is very simple. We'll restart it. So as you can see here, they're operating pretty intelligently. They have a sensor. It's a raycast. They're able to see in a direction at pretty much an angle. So they use this to identify each other as well as food that they're going to go eat. All of this just evolved naturally over the course of several generations, several hundred probably. So that's that. And zoom. All right, so we have another video, and this time it's the same simulation, but with walls. And the entities learned how to navigate around the walls to find the food. They also learned something very interesting that I will point out as soon as I find my mouse. All right. So notice over here in the corner, they're actually following each other. This is pretty cool. This is a social behavior that we're witnessing. And later on in the simulation, you'll see them run around up here just in a circle, continually following each other. It's a learned behavior that pretty much guarantees, or not guarantees, but increases the chance of them finding food and effectively having offspring. So I'm working on a life simulation as well, and I'm working with a very talented developer. His name is Nash Worth. He's creating some 3D worlds in the web browser, and I've got a demo of that too. So these aren't artificial networks. However, they are some interesting concepts that he discovered as he was creating this. So we have a bird here in the middle, and this bird is trying to find all of the different bugs. Right now the bird can't do anything, but we need to turn on some of the functionality. So we're going to turn on hunting, and if you notice, it's starting to track and then run after it. Unfortunately, that's not enough to be able to catch up to those bugs, which are pretty fast. So we need to introduce a pouncing activity. So this pouncing activity, it uses energy in exchange for the potential to gain energy. This could be an example of an actuator that we evolve over time. Pretty cool. So if you would like to be notified when this 3D simulation comes out, I have a newsletter that you can sign up for on my website. Thank you very much. I appreciate this. And neural networks are definitely going to be an increasing part of our life, increasing part of our architectures as we evolve our technology. So thank you.